Hey, welcome back to the most curious corner of the internet. Here, every tiny fact rewires the way you see the world, one spark at a time. A quick flash of light cuts through the dark. Alright, let's jump into today's surprising twist. Look up at a skyscraper on a windy day. It looks calm, solid, unmoving. But here's the truth. That building is moving right now. Swaying, breathing, quietly negotiating with gravity, wind, temperature, and sometimes earthquakes. So the real question isn't how skyscrapers stand tall, it's how they don't fall down. Today, we're stepping inside the hidden engineering that keeps the tallest buildings on Earth standing against forces strong enough to tear bridges apart. No hype, no sci-fi, just human ingenuity pushed to the edge of physics. Here's the uncomfortable truth. The taller a building gets, the more it wants to fail. Gravity pulls straight down. Wind pushes sideways. Earthquakes shake everything at once. Temperature makes materials expand and contract every single day. At small scales, buildings survive by brute force. Thicker columns, more steel, more concrete. But skyscrapers live in a different universe. At extreme heights, too much rigidity becomes dangerous. Structures that are overly stiff don't bend, they snap. That's called brittle failure. Modern design codes like ASCE 7 embrace a smarter idea. Controlled flexibility. By allowing inelastic deformation, skyscrapers dissipate seismic and wind energy instead of absorbing it all at once. To survive, tall buildings must move, just not too much, and never at the wrong rhythm. Skyscrapers aren't guessed into existence, they're tested relentlessly. Engineers build detailed scale models, often 1 to 400 or 1 to 500, and place them in wind tunnels. Artificial storms recreate real atmospheric boundary layers. Pressure sensors map how wind wraps, separates, and slams into surfaces. For even higher precision, labs use high-frequency force balance systems. These measure tiny rapid fluctuations in wind pressure critical for predicting vibration and acceleration felt by occupants. And today, physical testing is only half the story. Engineers also rely on computational fluid dynamics, or CFD. Massive digital simulations that model turbulent airflow in 3 dimensions. Projects like the Shanghai Tower combined CFD with wind tunnel testing to predict sway, torsion, and vortex behavior long before construction began. The goal isn't to eliminate motion, it's to choreograph it. Now for one of the most elegant ideas in modern engineering. The tuned mass damper. Inside Taipei 101, there's a massive steel sphere, 5.5 meters in diameter, weighing 660 metric tons, suspended by 92-meter-long steel cables. This isn't decoration, it's precision physics. Every skyscraper has a natural frequency, typically, approximately between 0.1 and 1 Hz for very tall towers. For Taipei 101, it's around 0.15 Hz. When wind or earthquakes excite that frequency, motion amplifies. A TMD is carefully tuned to that same rhythm. When the building sways one way, the damper moves the opposite way, stealing energy through viscous damping. The result? Less motion, less stress, more comfort. And it scales up. 432 Park Avenue uses a damper system exceeding 1,200 metric tons. It's not resisting nature, it's cancelling it out quietly. At street level, skyscrapers stop pretending to be delicate. They rely on mega columns. In towers like the Burj Khalifa, individual columns can carry loads of up to 2 million kilograms per column. Together, that adds up to millions of metric tons distributed safely through the structure. These columns work with a massive reinforced central core, forming a stiff but flexible tube-like system. The perimeter resists wind. The core controls torsion. Outriggers help them work as one. It's not one structure, it's a coordinated system. Forget the concrete you imagine. Modern skyscrapers use high-strength concrete and ultra-high-performance concrete, or UHPC. UHPC regularly exceeds 150 megapascals in compressive strength. It contains steel or synthetic fibers that improve ductility and control cracking. But here's the key detail. Modern towers aren't concrete instead of steel, they're hybrids. Steel handles tension, concrete handles compression, fire resistance, and mass damping. Buildings like One rely on composite systems, because at extreme heights, balance beats brute force. No skyscraper starts in the sky, it starts underground. Some towers use deep piles, drilled directly into bedrock. The Burj Khalifa uses over 1,500 piles, each about 50 meters deep. Others rely on massive mat foundations, concrete slabs up to 5 meters thick, spreading loads across entire city blocks. In soft soils, like parts of snow polo, engineers often use jet grouting, injecting high-pressure cement to stabilize weak ground. Foundations don't just carry weight, they resist overturning. They absorb seismic energy. They quietly save lives. Here's the secret most people never notice. Wind doesn't just push buildings. It creates von Karman vortex shedding alternating pressure waves that can lock into a building's natural frequency. That's dangerous. So engineers fight back with geometry. Tapered profiles, setbacks, rounded corners, spirals. The CCTV headquarters disrupts vortex formation through its unconventional shape. Other towers use outriggers' giant structural arms, linking the core to perimeter columns to control torsion. Sometimes, the strongest defense isn't strength, it's confusion. Skyscrapers don't survive by refusing to move. They survive by knowing how to move. They bend, they absorb, they adapt. Every tall building is a quiet agreement between physics and creativity, and every day it stands. That agreement holds. Thanks for hanging out till the end. Love having curious minds here. If this sparked something, hit like, subscribe, and tap the bell for the next drop of wonder. And if you're still in discovery mode, pick another video. It gets even better. See you in the next one.